This is a joint project with Esther Vidyasik from the University of Hawaii at West Oahu. Actually, she motivated, I should say, my interest in studying this problem, because I realized that we can use Teixeira singularity in order to prove existence of cycles in her model of glacial cycles from climate modeling. And that's why I got interested in proving the existence of those cycles and stability. Okay, so let's begin. Some preliminaries first. In this slide, I give definitions of two possible new equilibria, which are new for discontinuous systems. Assume that you have just three-dimensional system like this, and u equals 0 will be a switching threshold. So when the variable, this last variable u, crosses u equals 0, the index of my functions, the index of the right-hand side, switches from plus to minus, from +1 to -1 and back. So I have two smooth systems on the two sides of switching threshold. First of all, the concept of switched equilibrium. The switched equilibrium is a point on the switching threshold where the vectors of the two smooth vector fields pointing opposite one to another, opposite, either directly towards one another or outwards one another. So such a point is called switched equilibrium in control. I think in our non-smooth dynamical systems, this point is called, how it's called? How it's called? Probably someone can help me. It's not really virtual equilibrium. It's called non-smooth equilibrium. But in control theory, it's called switched equilibrium. Then Teixeira singularity. This singularity is also called U singularity, but I came from UK, from the UK community. In the UK, they always call it Teixeira singularity. And so that's a point on a switching threshold, U equals 0, where the vectors of the two smooth subsystems are tangential to the switching threshold. In my case, tangential means the H component vanishes, because my switching threshold is U equals 0. Therefore, tangential, in my case, the vector field tangential to the threshold means H component vanishes. So these two conditions is the definition of Teixeira singularity. And this condition is the definition of switched equilibrium. So now what this picture is saying, this is plotting in xy coordinates. The blue curve is the curve of points where H plus vanishes. The green curve is the curve, this green curve is the curve of points where H minus vanishes. So when the point where these two curves intersect will be the point where both H minus and H plus vanish. So this point will be Teixeira singularity in the switching threshold. Okay, so this plane corresponds to U equals 0. So this is U equals 0. Now what this red curve is? The red curve is the set of all points x, y in the plane U equals 0, where I can probably draw here, where these first two the two-dimensional vector from the left-hand side here is parallel, or yeah, I'm just considering parallel, pointing towards or outwards or parallel to another, to the two-dimensional vector formed by F plus and G plus. So we can draw this curve. This red curve is not necessary. This red curve in U equals 0 is, of course, not necessarily a curve of switched equilibrium, because only first two conditions hold. This, if you consider the all three dimensions here, then you won't necessarily get the left-hand side is parallel to the right-hand side. Not necessary. So the points of this red curve, they are not necessarily switched equilibria, of course, but they will be a point from this red curve will be a switched equilibrium if this component number 3 vanishes. If the component number 3 vanishes here. And component number 3 vanishes means you have Teixeira singularity. So basically now I want to consider this situation, and generically you see, of course, we shouldn't expect that both H minus A and H plus vanish on the red curve, because you see, usually we can expect that blue curve, for example, intersects the red curve. So H plus component will vanish here, but H minus component will not vanish. H minus vanishes here. But I will consider the situation where both these curve, green and blue, intersect one another at a point which is on the red curve here. So I will consider the case where when this black point is on the red curve. This will mean Teixeira singularity is also a switched equilibrium. Those are different concepts. Generally, Teixeira singularity is not necessary a switched equilibrium, and switched equilibrium is not necessary a Teixeira singularity. So I consider the case where they coincide. And I will study bifurcation of limit cycles from that special point. I'm going to draw it in a second. So there is one paper that I found. Probably Brazilian group has more, and I'm sure that when I started working on this problem, I was sure that someone, of course, already studied bifurcation of limit cycles from Teixeira singularity. And I think I even heard some talks about that. But my goal was to study bifurcation of those cycles, specifically in the model which I got from a colleague, Esther Vidyasik. Okay, this next slide explains why this particular singular situation where switched equilibrium coincides with Teixeira singularity, why it's of practical interest, and how it appears in the model of climate change. In the, I should probably say, in the model of glacial cycles. Here is the reference. So what happens in that model? The equations look like this, where there are two temperature regimes, T plus and T minus. If you, I here opened even the paper for you. So this is the paper that I'm referring to. So it says in the conclusion, you can read that literally. So let me show you. Introducing two distinct climate states, one corresponding to glacial advance and the other to glacial retreat, we formulated equations as a Filippov system with a two-dimensional plane forming the discontinuity boundary. So you see it says two distinct climate states. Distinct climate states. So one climate state corresponds to one temperature, another one corresponds to another temperature. And also equations change slightly depending on whether you have melting or progression of ice. So it means that we have two parameters in our equations. One parameter in the one smooth subsystem, which is T plus, for example, and another parameter in the another smooth subsystem. And changing these parameters, T minus, oh, here's the written, T minus and T plus, we can move. We have control of the blue and green curves. And so in particular, we can, by varying these parameters, oh, okay, this one is supposed to be T minus, okay, this one is T plus. So by varying these parameters, these two curves will move. And eventually, for example, if we will keep T plus fixed and will vary T minus, then we can move this green curve until it finally reaches until the intersection with the blue curve will appear exactly on the red line, on the red curve. So this is pictured in this slide. So by varying this parameter T minus, we can reach this situation here where all three curves that I introduced earlier intersect at a single point. And those parameters I will call some initial parameters, bifurcation point, T0 minus T0 plus. And now I will perturb these two parameters. It's written here. I will consider perturbations of these two parameters and will try to prove the occurrence of limit cycles from this point. Maybe if there are any questions at this point before I go into mathematics. Everyone still hears me? Oh, yeah, probably.
Yes, we are here.
Yeah, very good, very good. You know, that's an instinct because we are teaching online, and from time to time I'm double checking with students. Do they still hear me?
Yeah, that's normal.
Okay. Now let's go into mathematics. So how we prove the occurrence of cycles? First of all, we need to introduce a time map. A time map will be a map that it takes for a point with an initial condition here, x, y, with an initial condition in the u equals 0. Okay, let's say this is u equals 0 plane. The time that it takes for a trajectory that starts here to make this little loop and intersect u equals 0 again. So this is a time map which we denote t plus of x, y, epsilon. So it means that we have to solve this equation. The third component, u variable vanishes. We have to search for times when the u component of our solution vanishes. U component vanishes means solution intersects the switching threshold. Therefore, this is the equation that we have to solve. So how we solve it? Here I show the Taylor expansion for of second order. So starting from 0, then first derivative times capital T. Okay, so this was supposed to be capital T here, capital T. So then the derivative with respect to time. So Taylor expansion. So here you see Taylor expansion. Capital T here. Oops. Oh my goodness. I wanted to draw here capital T. So then what we do with this initial Taylor expansion? First of all, we observe that this first term is 0 because 0. 0 because we expand about t x y epsilon equal 0. We expand about this point. Term just vanishes. Then this second term will also vanish because this is the time derivative of u, and time derivative of u is h, and h vanishes at the origin. I forgot to mention that now I moved my special point to the origin. I introduced a change of coordinates and moved my special point, which is simultaneously Teixeira singularity and switched equilibrium. I moved that point to the origin. Therefore, this first coefficient will vanish because it will be just h at 0, hi at 0, because and you see because this point is Teixeira singularity, this component will vanish, and therefore what my initial approximation that I will consider, I will improve this approximation. I will see later what I need from that approximation. These terms will be insufficient, I should say upfront. But right now we can view these as our first attempt, and we can equal this to 0, and this might be considered as our first approximation for the time map. Here is the time map. Now, what is happening with this coefficient? So how we compute this double derivative with respect to time at 0? So we differentiate first time, then we get I want to make some computations because my talk is full of derivatives of the general solution with respect to the variables. Those of you who are not familiar with that, for those of you who are not familiar with this derivative, let me make some simple computation right now, one time. Let's see how we compute this coefficient, for example. So we need two derivatives of the general solution. We know what? We know that u prime from this equation here, the derivative of u with respect to time will be h, let's say ui, hi. Now the general solution, capital X, comma, the general solution, capital Y, comma, general solution, capital U, and epsilon. Now we need second derivative here. So we differentiate this equation once again with respect to time. Therefore, in the left-hand side, we will get u I t t. And in the right-hand side, I now use multivariable calculus of several variables. So this will be the derivative of h with respect to x times chain rule, the derivative of x with respect to time plus derivative of hi and I here with respect to y times derivative of y with respect to time plus derivative of h with respect to u times derivative of u with respect to time. And this term, derivative of x with respect to time, this is what I know. It comes from this first equation. For this f goes here, because the derivative of x is given by this right-hand side. Then g goes here, and finally h goes there. So, and then I plug zeros. I plug zeros everywhere. So first substitute the right-hand side and then plug zeros. And then what happens for this particular term here? So this will be f, f, and f at 0 will be 0 because the origin is the switched okay. So I forgot to mention this condition. So in this climate model, the way how the switched equilibrium occurs, so we need that f minus at 0, g minus at 0 to be oppositely directed to f plus of 0, g plus of 0. Then origin will be switched equilibrium. The way how this condition is achieved in the climate model, and I apologize, there is no I here. In the climate model, this first right-hand side doesn't depend on the index. It's the same for plus and for minus. And therefore, if I assume that f of 0 vanishes, and that's exactly what we can find in the climate model, then this condition will be satisfied. Then origin will be a switched equilibrium. So I have this condition, and because of this condition, this term will vanish. This term here will vanish. Vanish. Now this second term will stay. It will be a g, this function g, and this component will vanish because this will be hi at the origin, and hi is Teixeira singularity, vanishes by this condition. So this term vanishes as well. So the only term that remains here will be this middle term, which is here. So this green term here will be the value of this coefficient. If we do some, if we make some observations, if we do some constellations. Okay, so I did that exercise once. I won't do computations of this type in the future in this talk, just one time. And this also tells us a very important property that we will use in the future. So then what we get for the time map, you see that the coefficient in front of capital T here coincides with the coefficient in front of y. Therefore, if we divide everything by this coefficient, then we get this formula. We get this formula where this y here doesn't depend on plus, on whether you consider your plus system or minus system. So this will be helpful. Okay, so what I wanted to stress as well, this result and these computations have been made several years ago, maybe like 3 years ago, and I didn't publish these results yet. And the reason, maybe main reason why I'm still postponing this is because I'm not fully okay with how I'm able to present the computations. Because you see here, I'm saying something interesting happens, and I will use this interesting later. The fact that I don't have the coefficient in front of y doesn't depend on the subsystem will be very helpful to me. But this is just algebraic. And for several results from here, I don't see geometric intuition. And that's why maybe some of the people from the audience, if have some geometric intuition into that would be great. For something specifically for this presentation, I made another attempt, and I made a progress in geometric intuition, and you will see my progress later. But for some facts remain fully algebraic. I don't understand the geometry behind some of the facts. Why that happens from geometry. Okay, let's go to the next slide. So that's what we obtain. The first approximation, this equation is the equation that we will use later. So this is the equation of the first for the first approximation of our time map. Here is a time map. These coefficients can be computed. These coefficients are given. So of course, these coefficients define this coefficient, the coefficient in front of x and the coefficient in front of y defines the slope of this dashed line, tangent line to the curves where h vanishes, where the third component vanishes. Why? Because if you start from any point on this green curve, then it will take 0 time for the solution to return back, because since this is h plus equals 0, solutions make small loops everywhere here, little loops here, small, bigger loops there, and closer we come to this line, smaller the loops are. And along this curve, the time it needs to get from the plane back into itself is 0. So time map is 0 along this line, and time map is 0 along this line. Therefore, what we have here in the first approximation, these are slopes of this of the tangent line to the green and blue curves. Yeah, okay. I have some geometric intuition. Because I do my best to figure out what this algebra means geometrically. Okay. Now we can introduce, after we are done with the time map, we can introduce the Poincare map. The Poincare map is the map. So we start from this plane, go move in one smooth subsystem, then reach the threshold and move along another smooth subsystem until we return back to the switching threshold. So this black, blue, and this green point, these 3 points, these are the points from the switching threshold. So we can introduce the Poincare map like this. And of course, later, after we find fixed points of this Poincare map, we will still have to prove that this time here is positive. that this time is positive, that this time is positive, that the fixed points that we found lead to positive times here. In other words, correspond to forward. The Poincare map that we construct here corresponds to the forward propagation of the flow of the system. And that's not the only condition. Then we have to make sure that this first, that the blue piece, the piece of our trajectory which corresponds to the plus time map, occurs in the positive part, in the right subspace, in the subspace u greater than 0, because u greater than 0 is where the subsystem H plus must be applied. If we find a curve from a trajectory which starts at xy, if we find a trajectory of H plus, of the plus system, which starts at xy and lands here, but develops in the negative, in this negative subspace, then this trajectory does not occur in the real, in the actual Filippov system, in the combined Filippov system. This will be a virtual trajectory. Okay, so then I'm saying that after we compute fixed points, we still must check that these fixed points are real, correspond to real limit cycles. So how we compute fixed points? First of all, we observe that by construction, our maps P plus and P minus, I think it's called involution. So it means that if we start here, then our P plus map maps this point into here, and if we apply our P plus map again, then it will move this point back. So the map P plus is the inverse for itself. This is common for this type of situation when you work with Poincare maps. So it means what? It means this property here, this interesting property. And in particular, it means that if we want to study fixed points of the Poincare map, then now we want to study fixed points of this combined map, P minus of P plus, then studying fixed points of that map is equivalent to solving this equation. P minus equals P plus. Okay, so this will be the equation that I'm going to solve. I will solve that equation line by line. This equation is an equation of two lines. Poincare map is a two-dimensional map here, two lines. And I start with the second line first. Second line. Now what is happening here? I consider, I rewrite, I equal to 0 the second components of this equation and get this. Then I do what? I plug the second component of P plus and P minus is y. Therefore, I expand y a little bit for the moment. I will need more terms in expansion later, but for the moment, I take just this, plug into here, and then I get. Now I use that important property that I mentioned, because if you plug the time map, if you plug time map from here into my expansion, then this y will cancel with that y, and cancel not cancel no cancel. If I plug this, not cancel. If I plug this time map into here, then I will get negative y here. I will get negative y. Okay, let me write it down. So here I have negative y plus other terms, but I have negative y here, and same negative y for minus system and for plus system, negative y. Therefore, when I consider the difference here, one negative y will cancel another negative y. And that's how I get this first important property. So if I solve the second equation, then the linear y disappears. Quadratic y will be the first y which plays a role when I compute, when I solve this second line of the equation for fixed points. So this means that though initially I get here b1 plus, this means that I have to account for y squared term, because y term vanishes. Therefore, the first y term which influences anything will be y squared. So this is my initial approximation that I will use for solving my equation. And from here, I conclude that for as a solution of the second of this equation, let's just call this equation, corresponding to the second component, by equaling the second components, I get this equation, which defines this type of parabola. When epsilon equals 0. When epsilon equals 0, I get this type of parabola from the second equation. Any questions so far? Okay. Then let's continue. Yeah, I see that I have 15 minutes left. I understand. So then I equal the first equation to 0. Because it's very important for me to try to understand what is happening in here, hoping that maybe then later I will get some feedback from my Brazilian colleagues or
Yes, we are hearing you. Okay.
You're not hearing me?
No, it's okay.
You hear me?
Yes.
Excellent. Thank you. Okay, now first component. Again, I plug first expansion. First expansion just vanishes because f of 0 is 0, which gives me switched equilibrium. Therefore, I have to go for the next expansion, next step of Taylor expansion, I get this. And this means that after I plug time map, after I get time map from here and plug into there, then my initial approximation, I will later see whether I need more terms or not. But my initial approximation is this coming from the first equation. Then what I have here, what this red equation means. So first of all, by looking at this orange, I understand that first of all, first important observation, and that's again that's probably the second important place where I don't have geometric intuition. For some reason, the term between quadratic nonlinearity, quadratic y vanishes, and that's important. That's crucial. This is what allows to get some results here. So this term vanishes if we compute derivatives in Taylor expansion. Okay, let me not go into more details right now. So vanishes. This term vanishes. And now I have already this orange curve, this orange parabola. So I know that I'm supposed to look for fixed points along this curve, or perturbed, slightly perturbed this curve. I can restrict my attention on the points which are on this curve, or close to this curve, or on perturbed curve of this type. This means that I can address the situation where x over y is small. X over y is small. Of course, I do that rigorously, but now I try to get some geometric intuition to my algebra, to my rigorous algebra. So since I'm looking for points on this curve, I can assume that x over y is small. X over y. Then I can divide this like divide this by y. So this x over y is small. This x over y is small. Then x will be of order epsilon from this equation. We will see that rigorously as well. Therefore, this term is of order x over y, so it's also small. Then what we have from this red equation, if we plug epsilon equals 0? If we plug epsilon equals 0, then from this second equation, we simply get this term. This term is all that remains. X equals 0, provided that a2 is different from 0, of course. But if a2, this coefficient, is different from 0, then this second equation at the limit will give me x equals 0. X equals 0. So this line. So this is my understanding of what is happening in these two equations. So in these two equations, when I will now look for fixed points, what will happen is the perturbation of this limiting situation, where this line touches this parabola. So by perturbing this situation now, I will get fixed points. That's how far I was able with gaining geometric intuition about my fixed points. Now, here is some rigorous observations. So here we have this orange 4 equation. Then I applied implicit function theorem to solve this orange equation for x. So I get x as a function of y epsilon, and then I plug this solution to the red equation. and get an equation of this type. The first terms are of this form. And then now my goal is to solve this with respect to y. If I will be able to solve this with respect to y, then I will so find y as a function of epsilon from here. Then I can plug my y into here, and then I will also have x as a function of epsilon. So how I solve this? I introduce this change of variables. Y equals square root of epsilon p. After the change of variables, my equation transforms to this, let me circle it, this final form. The red, we can say that my original red equation takes this form ultimately. And where these two terms, this term here and this term there, do not depend on epsilon. Do not depend on epsilon. And this capital K and capital M, they of course combine coefficients A, A1, A2, some of them, some of A's and some of B's. And therefore, I can solve this new green equation using the implicit function theorem. So I can plug epsilon equals 0. Then I get this equation from here. I can solve it for p, and I will get two solutions. And I actually have another one, the solution number 3. You will see why. But first of all, I get these two. I get trivial solution, p equals 0, and two non-trivial solutions. And by applying the implicit function theorem, I realize that if I consider epsilon positive, then I must assume this will be my condition here. My condition for implicit function theorem to be applicable. M over K is negative. So then I get two solutions, and now I explain what is happening. The two solutions that I get, so this line moves if M over K is of the right sign. So the right sign means we have this situation here. So this situation here. Then this red line moves towards the orange line, or orange curve and red line move towards one another. But red line is not really a line. This equation, because when you increase epsilon, this strange polynomial is not, of course, a line. The line breaks as soon as you perturb this line a little bit, breaks into something like this. And the two fixed points that I discover are these 2 points. The greatest, the two bigger great points of intersection, this one and this one. So these are the 2 points that I can catch. And this is the point which corresponds to p equals 0, which I cannot catch. I didn't actually try much, but this method here doesn't allow to give any approximation for this point. And in my analysis, I need approximations. I not only need to prove the existence, but I also have to give a formula for the epsilon expansion, because in climate modeling, they want to know how exactly this the period of the cycle changes. So I need to provide an answer. So when you increase epsilon, how exactly the period of the cycle will increase. That's why I do this perturbation type of rigorous analysis. Okay, so I get these 2 points, and basically what? And then I have to study stability of these points, since I have, I presume, like 2 minutes left. Oh, no, almost. And I have one slide for stability. Okay, here is stability. Stability is not doesn't lead to serious conditions, to complicated conditions. If you make some important remarks, then we realize that if we consider the Jacobian of the Poincare map, I will go straight to the point since I have few minutes left. I think I made important emphasis in the past, spending more time on that. Now it's okay if I will be a bit faster. So Jacobian on the fixed point can be shown to be equal to this, can be shown to allow this expansion here, this expansion. And then it implies, if you look, if you observe, if you look at the expansion for the fixed points here, because this is the fixed point, this y double underlined is what happens with this y component of the fixed point under one loop. This is what is denoted double underlined. This single underlined is the fixed point. Double underlined is the image of the fixed point under the action of one piece of the Poincare map. So then this is the matrix, because these two y, they turn out to be just the first, the leading term here is just y and minus y here, y and minus y, and that's why this condition, in order to have all eigenvalues inside the unit circle, we need this to be negative and this to be negative. And therefore, we just get these two conditions. These two conditions, the first one comes from this being negative, the second one comes from this being negative. Okay, this is not supposed to be fully understandable. I was quite fast here, but the conditions that we get are quite simple for stability. And now the main challenge. Another last slide where you will also see my final remark. This is the last slide. This is the last slide where I list the constants. The computational formulas for all the constants which appeared in the past, in the previous slides. And you see that all, for example, I need A7. I need A7, what is A7? A7 is this, the component in front of the cubic term, the coefficient in front of the cubic term of the expansion. So I use the expansion of the first, of the X map, I need to use that up to the third order. And this leads ultimately, if I then want to compute those coefficients based on the right-hand side of the differential equation, then these coefficients, A1, A2, and the required coefficients, I don't need them all. I need only A2, A5, A7. So A7, for example, you see involves 3 derivatives of the general solution, then if I compute, they will of course give you closed form formulas in terms of the right-hand side, but these are very long formulas in terms of the right-hand side. And that's another thing that disturbs me. I still cannot understand whether this is exactly expectable, that we cannot do any real prediction without knowing that long constants, or I don't see how something cancels, why something cancels. But technically, this is done and applied to the model, and the preprint is here. So we checked, we computed all these coefficients for the model, changed checked that condition, that the assumptions hold, and so it's applicable. But why I'm postponing publishing this is because it's not very satisfactory for me from this understanding and mathematical beauty viewpoint. Okay, so thank you for your attention.